So the pH of most solutions changes significantly when you add an acid or a base. So if you think of pure water and you add some hydrochloric acid in it, the pH is going to drop. It's going to change dramatically. Buffers resist pH changes. And the essential part of a buffer is that it has significant amounts of a weak acid and the conjugate base. Or it could be vice versa. It could be a weak base and the conjugate acid. If you have just the weak acid or the weak base alone, it doesn't have enough of its conjugate to act as a buffer. So let's look at pictures here. So here we have a weak acid solution, acetic acid, and sodium acetate in solution. So sodium acetate is an ionic compound, right? If we remove the sodium ion, which happens when this dissolves, right? When this dissolves, the sodium separates from the acetate. The sodium's called a counterion. It's a spectator. It doesn't participate, but it is there. So we have acetate ion. There should be a chemical equation here. So H2C2H3O2 is a weak acid, and it ionizes to form hydrogen ion and acetate ion. In the buffer solution, we have significant quantities of both. Not just the acetate that forms from the partial ionization of the weak acid, but significant amounts of both. So when we add an acid to this, the conjugate base can neutralize it. If we add a base, the acid can neutralize it. So it can resist pH change regardless of what you're pouring into it. So let's learn to identify buffer solutions. Yeah.
So the previous slide, so once you add more of the sodium acetate, the percent ionization goes down for the acetic acid.
Sorry, I'm lost. I'm sorry, I was trying to find the slide. Can you repeat your question?
So when you add more of the sodium acetate
Mm-hmm.
to the solution, and you force the equilibrium back to the right? Does the
To the left.
or to the
You're
left?
pointing to the left and saying right.
This is my right, I'm left.
Yeah, okay. I am too, so.
So does that make the percent ionization go down for the acetic acid? Because it's not going to ionize as much, right?
Well, it would change the percent ionization when adding
More acetate ion.
yeah, we don't usually think of percent ionization in a buffer solution. We think of it more when we just have a single weak acid and we look at how much does this ionize. When you look at changing the pH or adding hydrogen or hydroxide ion and causing this equilibrium to go back and forth, yeah, you will be changing the percent ionization. Yeah. So this is a sort of question that could be on an exam. Which of these solutions is a buffer? Well, what is a buffer again? Weak acid and conjugate base, or weak base and conjugate acid. Strong acids and strong bases won't do this. So let's look at these. Sheesh. Feels like Monday, it's only Tuesday. Let's look at A. So HNO2, what kind of an acid is that? It's weak. What about this? That's a strong acid. So you got a weak acid and a strong acid, so that's not a buffer. Here we've got HNO3 and NaNO3. That's a strong acid, right? That is the acid in its conjugate base, but it's a strong acid, so it won't act like a buffer. And the reason is, with the strong acid, it ionizes completely. It ionizes completely. So if we add hydrogen to this, hydrogen ion to this, there's no equilibrium going on. We're just going to have more hydrogen ion. Because the conjugate base of a strong acid does not act like a base. It's pH neutral. So that one's not a buffer. How about letter C? Yeah, we've got a weak acid, but that's not the conjugate base. So that's not going to work either. What about this one? Yeah. Here we have HNO2 and NaNO2. So we can just ignore the sodium. That's nitrite ion. We've got HNO2 and we've got NO2 minus its conjugate base. Everybody see that? Because I can explain it more, but... So that's our correct answer for that one. So now that we know what a buffer is, we're going to learn to calculate the pH of a buffer solution. So let's look at acetic acid here. Acetic acid and sodium acetate, and this solution initially contains 0.1 molar of the acetic acid and 0.1 molar of the sodium acetate. So we could write that in here, although we're not really doing a calculation here yet. So the presence of this acetate here causes the acetic acid to ionize less than it normally would, right? Normally this would ionize and we'd have equal amounts of hydronium ion and acetate ion, and it would go according to the Ka for acetic acid. But by adding acetate ion, we affect the equilibrium. So by adding a common ion, we're changing the equilibrium. This is called the common ion effect. So adding acetic acid forms acetate ion, and then we're also adding acetate ion. So let's calculate the pH of a buffer solution that's 0.2 molar in acetic acid and 0.1 molar in sodium acetate, and we're given the Ka. So let's look at the chemical equation for this. Good grief. There we go. Oops. Someone save me, please. HC2H3O2. That's our acetic acid. And we're going to look at the equation that's represented by the acid ionization constant, the Ka. So we've got the acid ionizing to form H plus and C2H3O2 minus the acetate ion. And we know for this that Ka is equal to 1.8 times 10 to the minus 5. So we're going to make this into an ice table. Got initial, change, equilibrium. So we're given the initial concentrations, 0.200 molar and 0.100 molar. This is 0.1 molar sodium acetate. Sodium acetate dissociates completely. So we've got 0.1 molar sodium ions, which we don't care about, and 0.1 molar acetate ions. So I know there's no sodium in here. It's okay. So then we're going to have some change. Well, the hydrogen ion concentration, we're going to say, is essentially 0. So this can only go in one direction, right? What direction? To the right. Because we can't have less than 0 here. So the change must be plus x for the hydrogen ion concentration, so that it's plus x over here and minus x over there. So at equilibrium, we've got 0.20 minus x, and 0.100 plus x. Now we're making ice tables, and then sometimes we forget why we were starting this in the first place. What are we trying to calculate? The pH. So for the pH, what do we need? The hydrogen ion concentration. So as we ended up setting this up, X is going to be our hydrogen ion concentration. So that's nice. So 1.8 times 10 to the minus 5 is equal to X times 0.100 plus X divided by 0.200 minus X. So 1.8 E minus 5 on the one side. X times. Now, your calculator doesn't care if you put the 0 before the decimal point and these zeros after. And sometimes these get a little long and your calculator says, I can't handle any more characters. So then you can definitely cut those sorts of characters out. I'm getting 3.598 times 10 to the minus 5. That's my X. In this problem, X is equal to the hydrogen ion concentration. So pH is the negative log of that. 3.598 E minus 5, 4.444. Any questions? Probably really just two. If you're not sure how many significant figures to include, toss an extra one in. Looking at some of your labs and your worksheets, some of you are rounding off a little too much, and then you get some rounding errors. So it's better to have an extra digit or two rather than not having enough. So pH is 4.44. Any questions? So we can derive an equation that relates the pH of a buffer solution to the initial concentrations of the buffer components. Because hopefully that problem that we just did seemed fairly straightforward to you. Oh, we've got an equation, we've got initial concentrations, ice tables, solve the thing, and there we go. So you can imagine that the process would be really similar for lots of different buffers. So there's an equation called the Henderson-Hasselbalch equation that relates pH of the buffer solution to the initial concentrations. So we can derive this.